Today we will talk about a well-known theorem in algebra called the Hilbert basis theorem. And we will stick to the traditional setting of a commutative ring with identity, although the result itself can be generalized in an obvious way to the non-commutative setting, which we will indicate at the end of this video. In order to understand the assertion of the theorem, let's review some basics. A ring R is called a Noetherian ring if any ascending chain of ideals stops growing with respect to inclusion at some point, at some index. That means if you have a bunch of ideals like this, then they will stop growing by inclusion at a finite index. A well-known example is the ring of integers. So here's what the theorem says. If a ring R is Noetherian, then so is the ring in one determinate, the polynomial ring in one determinate over R. The ring of polynomials over with coefficients coming from R and with only one indeterminate. That's Noetherian too. Before we go into the details of this, let's note a couple of obvious or easy to get corollaries. If R is Noetherian, if we apply the Hilbert basis theorem repeatedly, you get that the polynomial ring with n indeterminates over R is Noetherian as well. Well, to see how this is done, let's just note that, for example, in the case of two indeterminates, this ring is isomorphic to Rx1 and the polynomial ring over it with x2 as the indeterminate. So these two rings are isomorphic in an obvious way, so that if R is Noetherian, then so is Rx1 at first, and then upon a second application, so too is Rx1, x2. As for the second assertion, let's remember, okay, so what does it say? It says that if S is an extension of R generated by R and finitely many elements of S, say A1, A2 through AN, then S is Noetherian too. That's easy because there's an obvious evaluation map from this ring, Rx1, x2, xn, onto the S, the ring S, via evaluation. It takes every polynomial f and maps it to the polynomial, the value of the polynomial at the tuple a1, a2, an. That's the ring epimorphism between these two rings, and Noetherianity is invariant under ring epimorphisms. So, number 2 follows. Okay, now we can prepare a little bit toward the proof of the theorem that we will present here. First, we need to note basic instruments that we'll be using. We need a tool to pass from ideals of Rx, the polynomial ring, to the ideals of R, the base ring. And one such tool is In, where n ranges among the whole numbers. So for a given ideal A of Rx, In of A means, is the set of leading coefficients of the nth degree polynomials in A and 0. If there is no such polynomial, then you choose 0. So In is an ideal for any value of n, and here are some important properties for us. If A and B are two ideals with A contained in B, then their INs bear the same inclusion relationship for each value of n. And In of A is always contained in the In plus 1 of A. This may be the rather non-trivial one to see, but maybe I should say rather it's the less easy one to see. So, okay, let's see it. Take any element here. Then there's a polynomial, let's say b. Okay. Then there's a polynomial f with b as its leading coefficient. And if you multiply it by x, you get an element of a still, because a is an ideal. But this time b shows up as the leading coefficient of an n plus first degree polynomial, which means b belongs to in plus 1 of a. Okay. And here comes the most important instrument for our proof of the theorem. Again, in the same setting, when a and b are two ideals with a contained in b, their equality is equivalent to their in values matching. Their in's coinciding for all values of n. Well, the rather non-trivial part in this one seems to be this direction, from which is the one that we'll be using really. So to see that, choose any. Okay, if assume the right hand side of the equivalence, and assume contrarily that a is not equal to b, then you could choose some polynomial in the difference of a with the least possible degree. Let's call it f. Let's say f is in this form, and am is its leading coefficient. Now our hypothesis says ims of a and b are equal, which means there's some polynomial, say g in a, with the same leading coefficient. But then the problem is f minus g cannot be an element of b minus a, because if it were an element of that, then so would be its sum with g, which is f. That would be a contradiction. Therefore, this now goes, the presence of this in the difference of b and a contradicts the choice of f as a polynomial with minimal degree. So this means a is equal to b. Now we can prove the theorem. Take any ascending chain of ideals in the polynomial ring Rx, and taking the in's of the terms of this chain, we can form a mesh like this. So look at this mesh. What happens here is that the first row, for example, consists of the sequence on the first row consists of I0 values of the a case as its terms, and the second one is obtained by taking the I1s of the sequence AI. So this way we form a mesh, and here's what we want to do. We want to be able to use the one of the prior results that we mentioned. What was that one? It's this one. In order to be able to use this one, we aim to show that this mesh stops growing in any direction at some point, which means there is an index after which all the columns consist of equalities. Okay? So to do that, okay, let's first apply Noetherianity to get a termination point for each of the rows. Now since these are ideals, all the terms of this mesh are ideals of R. By Noetherianity of R, each of these rows stops growing at some finite index. Our claim, which is the crux of the proof, is that there's an upper bound for such indices. Now note this though. As you move along the mesh to the right and downward and zigzagging like this, you will be traversing a path of inclusions, not necessarily proper in general, but it will be a path of inclusions. Okay? All right. So that's what will be happening. Now, okay, so back to our claim. There's an upper bound for such indices. What if there were none? Then I'll simply read the slide that I think says it all. We could find a path zigzagging to the right and downward on the mesh, along which there would be infinitely many proper inclusions. That would go against Noetherianity. But if you're not convinced of what it says, convinced about what it says, let's just work it out. Let's work out at least the inductive part of this observation. If we didn't have that upper bound mentioned earlier, then here's what would happen. Let's say the first row would stabilize at the end first index, whatever that index is. Then this is what happens, right? This is what you see on the screen, this is what happens. Okay. Now, since there's no upper bound by hypothesis, the one that we've just adopted, then there's another index, n2, which is strictly larger than n1, at which step a row that's further below will stop. In other words, there will be a row number k, which will not stop until it reaches this n second index. So here's that gives us a proper inclusion. Okay. The real inductive part is this. There are infinitely many indices greater than n2, by which step, and not any earlier, some rows stabilize. So infinitely, this means what? This means infinitely many rows below, okay, let me not say below just yet, infinitely many rows stop later than the n second point. Since there are infinitely many such rows, they can't all be squeezed between the first and the kth rows. So some of them, at least one of them, must occur after the kth row. What this means for us is this. Of course, you go down and to the right, once again, to find a tth row, which is further down, further below the kth row, and which stops later than the kth row does. This was the inductive part. So if you apply it repeatedly, namely if you use the induction, it tells us that we can form a sequence, an infinite sequence of proper inclusions between ideals. That's again against the Noetherianity. So the claimed upper bound, a claimed upper bound exists. So let's say n is one such upper bound. What this means is at the nth step or index, all rows will have stopped growing already, and we will have our our columns consisting of equalities alone. If you recall the previous observation that says, in this situation, let's say an is equal to an plus 1, or not an, I should say an. Yeah, an is the right one. If all the IKs of these guys are the same. But this is what this picture tells us, right? This previous picture is exactly what it tells us. Okay, so this implies finally, that all the ANs, all the ideals, an plus 1, an plus 2, they are all equal to each other by application of this result that we have quoted from earlier. So this proves the theorem. This is it's not really that hard to understand. I just try to explain the proof in detail. And here is the obvious generalization of it to the non-commutative case. So thanks for listening.